Hello, this is Mr. White, and this video is on implicit differentiation, part 1. Here are the two exercises we'll do in this video. Before we even get into the calculus of this first exercise, let's just try to get a sense of what this must look like without even using a calculator. All right, well, if I were to let x equal 0, then y to the fourth would have to equal 16, and that means y must equal 2, right? So I'd have a point right here. But wait a minute, y could also equal -2, because -2 to the fourth power also equals 16. Similarly, I could determine that if y were equal to 0, then x would have to be plus or minus 2. Okay, the most convenient points are taken care of. Let's then ask ourselves, what if x equaled 1? Well, then that would mean that y to the fourth would have to equal 15. Well, I know that 2 to the fourth equals 16, and I'm guessing that whatever y must be here must not be too far off from 2. So it'll just be a tiny bit less than 2. So that was if x equaled 1. That means that y is a little bit less than 2, so we'd have a point maybe right around there. Same thing if x were equal to -1, and we could also have the y values themselves be negative, and we could continue along that kind of thinking, and just by plotting a number of points, start to get a sense of a shape there. We kind of get the sense that's going to be roughly straight here, not perfectly straight, but roughly straight, and then as we get closer to the corners of this shape, it's probably going to curve a little bit like that. So again, I just want to encourage you to recognize that without too much trouble, you can get a sense of what a shape looks like. All right, let's now do some calculus on this and figure out what would the slopes of these tangent lines to this shape be. With implicit differentiation, we're not going to bother trying to get y all by itself. We're not going to try to get y as a function of x. Let me just move this off to the side. We're just going to leave this equation as is and derive it in its present form. Now, before we actually do that, let me make one additional comment as well. Let me remind you that the implicit differentiation is really just an application of the chain rule. So consider for a second the function, let's say we had an outer function of blank to the fourth power, and let's say we had an inner function of, I don't know, 3x plus 2. And we are planning to derive that. We're going to do d over dx of this function. Think of what we would get. We'd focus on just the outer function, and we'd say, if I derive that, I'm going to get 4 blank to the third power. And then I turn my attention to that inner function and say, okay, the inner function not only goes here, but then I take the derivative of that inner function. I'll do d over dx of that inner function. Now, I could have just written 3 right here, right? But I've got a bigger point to make here. If you totally buy that as an application of the chain rule, what's to keep us from saying that there's anything special about 3x plus 2? What's to keep us from just saying, I'm going to get rid of that 3x plus 2 in all 3 locations and replace it with y? And now we're starting to see that this is what implicit differentiation is, right? That if I take the derivative of y to the fourth power, that I would just derive it as normal. I'd apply the power rule and get 4y to the third power, but I also need this additional chain. This is the result of the chain rule. I need that dy over dx at the end. Similarly, one might ask the question, what if I just replace that with an x instead? Well, then the derivative of x to the fourth, this is nothing new to us. The derivative of x to the fourth is 4x cubed. And what about this last little piece? Well, that's just dx over dx, which just equals 1. And we don't really have to write it, correct? So this just looks like our regular non-chain rule deriving. Okay, I hope you're seeing the connection between all of these. Again, implicit differentiation is an application of the chain rule. So let's go ahead and apply it here. Since I basically just worked it out here, Let's use the results of that and say that when I do the derivative of both sides of the equation, x to the fourth plus y to the fourth, and then the derivative with respect to x of 16, I'm going to get 4x to the third. And again, this is where a moment ago I had a dx over dx, but then I said we don't really have to write that, correct? However, when we derived the y to the fourth, we saw the effect of the chain rule. We saw that we not only got 4y to the third, but we had dy over dx. And over here, the derivative of constant will always be 0. All right, so what do we do now? Let's get the dy over dx by itself. So even though in the original problem I didn't have to get y by itself, I do want to get the dy over dx by itself. Think of this as a variable in its own right, and we just need to isolate it. So I'm going to subtract this 4x cubed over and then divide by the 4y cubed. And that would give me dy over dx. I subtract the 4x cubed over and then divide by the 4y cubed. And then I realize that the 4's go away, and I just get negative x cubed over y cubed. And I put a box around it. But I'm not totally satisfied unless you have a real clear sense of what we've just done here. So I'm going to bring up my GeoGebra construction of this curve. And sure enough, it looks like what we speculated it would. And I see that I've already got a point created that I can just ride along the edge of this curve, and I can see the tangent line adjust accordingly. And let's make sure we clearly understand what the derivative does for us using implicit differentiation. I'm just going to stop at some random point here. X equals 1.34, y equals 1.89. Let me move this over so that I can see the derivative there in the background off to the side. And let's figure out what the slope is going to be at that point. Notice that now with implicit differentiation, unlike what we've become accustomed to, with implicit differentiation you need to know both the x and the y value. So let me see if I can squeeze this all onto here. All right, let's calculate the derivative. And again, it's going to be negative x cubed, which in this case is 1.34 cubed. Now I should point out that this is rounded off, of course. I'm not expecting absolute precision here, but roughly 1.34 cubed over or divided by the y value cubed, which is roughly 1.89 cubed. And let's see what we get. We got negative 0.356 approximately. Negative 0.356, remember that. And let's go to GeoGebra here. And let's bring up the tangent line equation. And I see that it's negative I could definitely see that the slope of that tangent line is negative 0.36-ish, again, within round-off error. So I hope you clearly see what the derivative has done for us. At any point along the way, all I have to do is go to the derivative, the negative x cubed over y cubed, and plug in the respective x and y values, and I would get the slope of the tangent line. All right, let's go on to the next exercise. Once again, we'll use implicit differentiation to find the derivative of this function, x squared y plus y squared x equals 32 minus y. And it would be rather difficult, not impossible, but rather difficult to get y by itself here to define this explicitly. So again, we're just going to let it be. We're not going to shuffle anything around. We'll jump into the differentiation. And I'll spare you any attempts to try to figure out what this is going to look like without the aid of technology. Let me just bring GeoGebra up here. And we'll see we have a rather interesting looking function there in blue. And again, in pink or magenta, I've got a point riding along the curve and it's red tangent line, and I can see that, again, I can see the tangent line adjusting as I ride the curve along the point along the curve. All right, so we want a derivative expression that will allow us to calculate the exact slope at any of these point values. Let's get to it. All right, on the AP exam as well as on my test, just to be perfectly upfront, anytime you're given an implicit differentiation problem, it's very likely you're going to have to employ the product rule. because it doesn't take much to do implicit differentiation just on like the last exercise, but when you have to use the product rule, that's what really shows whether you know your stuff. So let's recognize that x squared is a function of x, and we could think of y as a function of x. Y is changing as the x value changes, right? So y changes with x. It's a function of x. And therefore, these are two different functions of x, and we need to use the product rule accordingly. So, of course, the product rule says that I would take the second function in the product, the y in this case, times the derivative of the first, times 2x, plus the first function, x squared, times the derivative of the second. Now, how do I write the derivative of the second? D over dx of y, or dy over dx. Okay? That was the first product, and we see that there's a second product there as well. So similarly, I might suggest you pause the video and try it on your own and verify that it matches my answer. If we're going to do this product here, a function of x times another function of x, we'll employ the product rule, and we'll do the second one. Let me erase that. And we'll do the second function times the derivative of the first. Now here's where we have to use the chain rule. Okay, so just like we did in the last exercise, if I'm going to derive y squared, I'll go ahead and do my power rule and get 2y. But then remember how the chain rule came into play and gave us a dy over dx. Okay, pause and refresh your memory on that if you missed that point. Please do not go on if that doesn't make sense to you. Maybe look at your notes from the last example if you need to. So again, that was the second times the derivative of the first, plus the first times the derivative of the second. Just finishing up our product rule here. Plus the first times the derivative of the second, which in this case is 1. And I'll go ahead and write times 1 just for emphasis. And that all equals the derivative of the right side of the equation. So let me put an equal sign here. And if I derive 32, I'm going to get 0. And if I derive minus y, I'm going to get minus dy over dx. All right, take a deep breath here. What do we do from here? Remember from the last exercise that our next objective is to get dy over dx by itself. Treat it as if it's a variable in its own right. I need to get this by itself. But it also is present in the equation here and here as well, right? So how do I get a single dy over dx by itself? Well, I need to start by getting all of the dy over dx terms by themselves. So isolate them on one, or I shouldn't say by themselves, but I'll say together on one side of the equal sign. Since I've already got one of them over here, let me go ahead and move them all over to that side. It really doesn't matter. I could take this one and move it over to the left of the equal sign, or as I'm going to do, I'm going to take these two and move them over to the right. So obviously they bring some baggage along with them. Let's see what we've got here. I'm going to go ahead and document that minus dy over dx there, negative dy over dx, and I can tell I'm going to need to make some space for myself, so let me move this over. So I've taken care of this. Let's move this one over, and again, it carries some baggage along with it. That's all one term that I cannot separate at this time. So that will be subtracted over to the right side, and I'll get minus x squared dy over dx. And then I'll subtract this one over as well. Minus, and let's go ahead and combine that as 2xy. 2xy times dy over dx. So let's start by just getting all the dy over dx terms on one side. Notice these remaining terms do not have a dy over dx in them, so we'll let them hang on the left side of the equation. Those two right there. That's going to be 2xy plus y squared. Okay, and now to get, again, remember our goal here is to get dy over dx by itself, so let's factor it out from those terms on the right-hand side. So let's put dy over dx outside of some big parentheses there. And what goes on the inside of the parentheses? Well, negative 1, because dy over dx times -1 will give me this. And then I'll have minus x squared, because dy over dx times -x squared will give me the second term. All right, and finally, inside that parentheses, I trust you're getting the idea now, minus 2xy. And on the left side, I'm not going to do anything. We'll just keep that as 2xy plus y squared. And finally, as my last step here, I can get dy over dx by itself by just dividing this whole expression over to the left side. So I'm going to divide it over, and I'm also going to put the dy over dx first. So dy over dx equals, and it's going to equal this left side divided by this. So 2xy plus y squared all over -1 minus x squared minus 2xy. And if I prefer, which I kind of do here, it's a somewhat arbitrary choice, but since I see all those negatives down on the bottom, I'm going to factor that negative out. I'm going to factor that negative out. Watch how I do this. I'm not saying it's absolutely necessary, but if I have 2xy plus y squared on the top, and I'm going to factor out a -1 on the bottom, leaving a 1 plus x squared plus 2xy. Now again, I can think of that as having factored out a -1 here, but the way I'm going to write it instead is to just move the negative up here and get rid of that 1 and get rid of these parentheses. And then put a box around it and call it done. Did I have to do that last step? No, but I bet if this problem appeared in the book and you were to look in the back of the book, it would probably appear that way. Or I should point out, you might also see it with that negative distributed to the top. So we could also see a -2xy minus y squared without this negative in front. But trust you get the idea. Now, if I bring the GeoGebra construction back up here, I just happen to make sure that there would be at least one convenient point that we could check against. So for all these ugly x and y values, these ugly non-integer values, notice that 3, 2 is on this curve. So let's check that convenient point. The problem didn't state that I had to do this, but I always think it's a good idea to do something to verify that your answer is correct. So I'm going to put at 3, 2, which we do know from the GeoGebra construction is on the curve. And we could certainly plug this x equals 3 and y equals 2 into the original function and verify that it fits the curve. That would, at that point, dy over dx would equal -2 times 3 times 2 plus y squared, which is 2 squared, all over 1 plus x squared plus 2 times 3 times 2. It doesn't take us very long to check and see that that's going to be, let's see, 12 plus 4. So that's going to be 16. Let's not forget that negative out front, over 1 plus 9, that's going to be 10, plus another 12, so that's going to be 22. So that's going to be, let's see, -8 over 11, which as a decimal is approximately -0.7272, or I'll just put -0.72 repeating. So let's see if that checks out against the GeoGebra construction. It definitely has a negative slope, right? And if I show the tangent line equation, I see a slope there that does appear to back up our answer. And if I really feel compelled to, I can even show more decimal places, and I can definitely see a 0.7272. And again, just like our graphing calculators, even GeoGebra, once you get way out there in the significant figures, is going to have some little discrepancies that, oh, and I even see that our point there is not exactly at 3, 2 anyway. But I would say this agrees with our answer, and we'll call it done.